Okay. Welcome everybody, and welcome to everyone tuning in online. Thanks for coming. It's our pleasure today to have Novak Karadžetović visiting from EPFL in Switzerland. Novak's just about to finish his PhD. He's working with Arjen Lenstra there, and at the moment he's interning with our friends from across the lake at Amazon. About to finish the internship there and then go back and finish up on his PhD. It's great to have Novak today to talk about Cyc channels, particularly because Cyc is our remaining candidate in the NIST standardization process, and this is really important work that's very topical right now to see how to attack and defend the Cyc scheme. So pass it over to Novak.
Thank you, Craig, for the kind introduction. So today I'll be presenting Cyc channels, zero-value side channel attacks on Cyc. So this is a paper that I worked on in collaboration with other people, with Luca Defeo, Nadia Elmrabe, Émeric Genet, Natasha Linard de Guaitachon, Simon Pontier, and Elise Tasso. And we will present it later this year at CHES in September. So I'll be talking about side channels, and I'll be talking about Cyc, and how to attack Cyc with power analysis side channels. So if you know about Cyc, I guess most of the people on the talk know, it's one of the post-quantum key encapsulation mechanisms. It is currently fighting to be standardized. So a couple of days ago, or a couple of weeks ago, NIST chose one algorithm to be standardized, which is Kyber, but Cyc is still alive. It's in the 4th round, and now is the time of analysis of side channels, and we have shown some weaknesses, how to patch them, and hopefully it'll go further through the next round or to being standardized. Cyc means supersingular isogeny key encapsulation. So essentially what it does, it computes isogenies between supersingular elliptic curves. If you don't know what isogenies are, that's not too important. I'm not going to discuss isogenies in the first part of my talk, but it is essentially similar to elliptic curves and similar to Diffie-Hellman. And for the attack that I'm going to present today, it's essentially same as elliptic curve Diffie-Hellman, with some differences that I'm going to explain towards the end. So elliptic curves, what are elliptic curves? These are geometric objects that are also groups. So a geometric object, it means that elliptic curve is a formula. It is a function x and y, which you can write like this. In particular, we use elliptic curves which are of the type y squared equals x cubed plus a squared plus x. And a is a variable which defines the curve. So for example, in Cyc, when a is equal to 6, you get one of the curves which is used in Cyc, one of many. A point on an elliptic curve is simply a pair of coordinates, x and y, which lies on the curve. So x and y which satisfy the formula. In this case, the point minus 1, 2, if you plug it in, it will satisfy the above formula. So minus 1, 2 is a point on the curve E0, but we will also be working with general curves with general A's. Elliptic curves are groups. What that means is that if you have 2 points, you can add them. So there is some operation like in the natural numbers. If you have 2 numbers, you can add them. Well, if you have 2 points on a curve, you can add them, and you can also compute the negative of a point. How do you do that? Well, there's a geometric way to do that. Like if you have a point P and a point Q, you draw a line, then you draw a vertical line, and the last point of intersection is the point P plus Q. There's also an algebraic way to do it. We're given a formula, and we're going to show that formula in the last slide. Now, if you can add points, you can also do other things with points, like you can compute multiples of a point by adding a point to itself m times. This is how you get m times p. And these are the main objects, the main parts of Cyc that we'll use today. So how do you compute these elliptic curve group operations? So if you have 2 points, P and Q, represented with their coordinates x and y, we want to compute P plus Q, where what Cyc does is it is smart. It doesn't do it in the standard way, but instead it tries to save up on space by representing these points with only their x coordinates. So P and Q are represented only with their x, and the y is dropped. However, if you do that directly, then you lose some information when dropping the y. So in order to be able to add these 2 points from only their x coordinate, we also need to add a third point, which is q minus p. And now if we have the x coordinate of p, the x coordinate of q, and the x coordinate of q minus p, then we can add p and q by simply computing this value. So we compute one multiplication, one subtraction, a square, another subtraction, another square, another multiplication, and then we divide these 2 values. Except that we don't actually do that. The reason we don't do that is because divisions are expensive. So if you want to divide, it's going to cost you a lot, and you're going to have an inefficient algorithm, and there are also going to be other security-related problems. So instead of computing divisions, what is done in Cyc, but also what is done in general in elliptic curve cryptography, is that points are represented in a slightly different way. We use projective coordinates. So a number of value x, xp, is presented as a pair of values, x and z. And what is particular is that this pair of values, their quotient is equal to xp. So you can think of natural numbers representing them as rational numbers. So 2 is equal to 2 divided by 1, or 4 divided by 2. So you save the numerator and the denominator of a number separately, and this is called a projective coordinate. And what's nice about projective coordinates is that you can compute things without dividing. You can multiply 2 numbers by computing 2 multiplications. You can add 2 numbers by computing a couple of multiplications and additions, but you can compute an inversion without computing anything. You just swap the numerator and the denominator, and you have the inverse of a projective value. So what's good about projective coordinates is that you don't need to divide, and you can speed up your algorithm. So what happens in Cyc? What happens is that this formula of adding 2 elliptic curve points becomes this formula. So there is an overhead. Instead of representing 3 points with 3 coordinates, we now represent them with 6 coordinates. But when you compute the addition, you just compute this value and the numerator and the denominator separately, and you save them separately. So you can speed up the algorithm. Now this is one property of projective coordinates, but it's not the main one that I'll be discussing about today. What is more important with respect to projective coordinates is that they allow some level, provide some level of defense from side channel attacks. You can think about the following. So let's say you have some value, which is a public value, a number, which is loaded into a computer, which is under attack. So it is being attacked. A power analysis is done on this computer. So this value is going to be loaded, stored. It's going to go through the pipeline. It's going to be operated on. And when it is being operated on, some power is being consumed. And the power consumption is proportional to the Hamming weight of the number which is being operated on. To put it in simple terms. So this is a threat model which is valid in most of the processors today. And this creates a problem. This creates a way to attack protocols. Why? Well, because if we have public data in the pipeline, and this data is operated on depending on some secret, for example, one secret bit, and this is what is done in Cyc. You have one secret bit, you use it to change some data which is public. Then we can simply make a guess on how that data will update, and then we can do power analysis to see if our guess was correct. Like if the power consumption was what we would expect it to be if some guessed value would have passed through the pipeline. So what we want to do, we want to defend from this, and we want that values which are being saved in memory, we don't want them to be known. We want to hide them. That is, we want to randomize them. And this is what projective coordinates allow. So one projective coordinate represented with a numerator and a denominator is not unique. It can be represented in many different ways. In particular, so xz can be also saved as lambda x, lambda z for any non-zero lambda. Why? Well, because the quotient is always the same. X divided by z is equal to lambda x divided by lambda z. Simple example, number 3, you can save it in memory as a pair 3, 1, or you can save it as memory as a pair minus 39, 13. And what's good about this is that you can essentially make sure that the numbers which are stored in your computer are completely random. So in the beginning, what Cyc did was it loaded a point represented as x, and it stored it in memory as little x and 1. So x was represented as x divided by 1. In other words, the capital X was little x, and the capital Z was just 1. And this was, or proposed, to be patched by randomizing the coordinates. What does that mean? That means you choose a random number, and then you multiply both the numerator and the denominator by this random number. And what happens now is that when this number is saved in memory, it is completely random. And when this number is saved in memory, it is also completely random. So once they enter the pipeline and start being operated on, the power consumption done when computing these numbers is random. Like you cannot, you lose this correlation between the power consumption and the values themselves. And this is true. So this number is completely random in all cases except for one. And that case is the case when the coordinate is equal to 0. And this is where the 0 values comes from in the title of our presentation. So if a number is 0, you multiply by a random value, you're going to get 0 again. And this was what we tried to exploit. And we formalized our attack in the following manner. So we want to force a target party, which is computing Cyc. We want to force it to compute some point which has one of the coordinates equal to 0. Because then we know how that will reflect to power consumption, and if we have access to power measurement, we can gather that information. There are two such points in Cyc. There is the point 1, 0 and the point 0, 1. So the first point is known as a point at infinity on elliptic curves, and the second point is particular to Cyc. It's a special point. Okay, so let me explain Cyc finally. What Cyc does. A typical execution of Cyc takes as input a triple of x coordinates of points p, q, and p minus q, as explained previously. And then a secret, which is a secret number, which is a random natural number. The party which computes Cyc does that in the three following steps. First, there is the initialization step, where these three affine coordinates are turned into three elliptic coins in projective form, and we can assume that they are randomized. Then these three projective points are funneled to a three-point ladder, which is something similar to scalar multiplication on regular elliptic curves. And we use them to compute a new elliptic curve point, the point p plus sk times q. This new point is called r. And then in the third step of Cyc, the point r is used to compute a secret isogeny. So starting from the starting curve, the target computes an isogeny to another curve, and this final curve is a secret, a common secret. So today I will only cover the attack on the 3-point ladder. However, in our work, we also did an attack on the isogeny computation, and I have some extra slides for that, so maybe after we talk, I can get into a little more details on the isogeny computation. So the 3-point ladder is, as I said, it is essentially scalar multiplication on elliptic curves. It works in the following way. So you take 3 points, you assign them to new 3 variables. R0 is Q, R1 is P, R2 is Q minus P, and then you go through all the bits of the secret key and you do the following. So if the secret bit is 0, if the secret bit is 1, you will add R0 to R1. If the secret bit is 0, you will throw it away. And by throw it away, I mean you will add it to the second variable, which is kind of a dummy variable. And then at every step, you double R0. And if you think about it, what happens is you take Q, you double it at every step, and then whenever a secret bit is 1, you add it to P. And it's not so difficult to see that the final outcome, this point P, will be updated to the point P plus SKQ, which is exactly the secret point which we were looking for. So the question which we posed ourselves was, okay, what happens during this loop? And how can we make sure that one of these 3 points, for example, the point R2, has one of the coordinates equal to 0 during the execution. So what happens at step K would be the main question that we pose ourselves. So our attack works in the following way. So we extract secret bits from the target party one by one. So first we attack the bottommost bit, then the first bit, then the second bit, and so on. And what we always do is that we assume that we have all k minus 1 bits in order to be able to attack bit k and to extract it. So let's start by assuming that we have like the first k minus 1 bits of the secret key, which are represented like this. If we know this value, then there are only 2 options in the 3-point ladder at step k. And these 2 options depend only on the kth bit. And if you develop the formula from the previous slide, you will see that the third bit is either going to be equal, the third point is either going to be equal to this value, which depends only on some known information, or it is going to be equal to this value if the secret key bit is 1, which also can be pre-computed, right? If we have PQ and we have the secret key, the known part of the secret key. And this leads us to the attack. So the attack works as follows. I want to extract secret bit K. I assume that I know all the previous secret bits. Let me compute a public key, a maliciously generated public key. It's made out of 3 points, QP and Q minus P. So I select Q to be a random point on a random curve. I select P to be equal to this value over here. And Q minus P is the difference of those 2 points. Compress them into a public key and send them to the target. Now the target starts computing the 3-point ladder, and at step K, the following thing happens. So the third variable, R2, is going to be equal to the point T, which was the point 0, 1, or 0 something random if there was randomization, if the secret key bit at step K is 0, or it is going to be equal to something completely random and non-zero, I can assure you of that, if the secret key bit is 1. So in other words, we get a 0 coordinate or a 0 point if and only if a bit of the secret key is equal to 0. So what do we do then? Well, we do power analysis. We measure the power consumption of the computer, we zoom in at the kth step of the loop, and then we see what happens. And then we make a guess. Was this a 0 or was this not a 0? And if we make a correct guess, we repeat, we go to the next bit. How does this look in practice? It looks like this. So this is actually not power analysis, this is electromagnetic signal analysis. So it's done even without touching the wires or the processor. So it is a bit weaker, but it is strong enough. So this is how the computation of the 3-point ladder looks. These are the first 20-ish steps of the loop. And this is the case where the value is non-zero. This, on the other hand, is the case where you get the value 0 at step 12, if I remember correct. So if you count these spikes, somewhere around here is step 12 of the loop, and you can see that the power consumption suddenly becomes kind of atypical because you have all zeros. Now maybe somebody's watching this presentation from their phone and they say, oh, but I don't really see the difference. It looks pretty equal to me. So I'm going to say, okay, don't worry. That's not all. There's actually more to it. There is another point with zeros. And this is the point 0, 0. And let me show you how to compute this point. So if you remember the formula for point addition, it looks a bit something like this. And adding 2 points, it depends on it has 3 inputs, P, Q, and P minus Q, or Q minus P. Well, when the point Q minus P is equal to the point T, which is the point 0, 1, or 0 something, then if you analyze this formula correctly, you will see that the point P plus Q will always be equal to 0, 0. Right. So, and how does this relate to the previous attack? Well, in the previous attack, we showed that if the secret key bit is 0, then the third point R2 is equal to the point T, to the point 0 something. And the point R2, it's a Q minus P. It is R0 minus R1. So what happens is that the point R0 plus R1, which is being updated in the loop, becomes 0, 0. And one might think, okay, this is nice. So instead of 1 zeros, I'm going to get 3 zeros. So this that graph that I showed before, it's going to have like spikes 3 times as large. Not really. Actually, there's much more than that. So the point 0, 0, it's kind of special. It's not a projective point. If you did projective geometry, you will say, oh, but there's not even a point. This is 0 divided by 0. It doesn't mean anything. Well, not only that it doesn't mean anything, but it has a very nice property. If you have this point as an input, it's always going to be an output. So whenever you compute something, if 0, 0 is one of the inputs, you can have multiple inputs, the output is going to be 0, 0. And this is nice because it leads to an avalanche effect. If you compute 0, 0 one time, then every other variable from that point on, written in your memory, saved in your computer, going through the pipeline, is going to be 0. So until the end of the computation of Cyc, you're only going to have zeros. And this is pretty easy to exploit using side channels. So if you think about it, you have to distinguish 2 cases. Run an algorithm, everything in memory is 0, or run the same algorithm, but the values in memory are random. And if you have access to power consumption, this becomes pretty easy to distinguish. So somebody might have noticed that on the previous slide, I have cropped this picture because we never did an attack by only looking for 1 0. We were looking for this avalanche of zeros. And over here, we had the first 0 happening. So that point T, the point 0 something, was computed here, and it led to an avalanche. And then from this point onwards, you can clearly distinguish the power consumption between having all zeros in memory, which is shown in the bottom slide, or having random values in memory, which is shown in the top.
This is just a single trace, right?
This is just a single trace. Yeah, this is a single trace at that. And this is only 20 steps of the double and add, of the 3-point ladder loop. This loop goes on for about 250 steps. So you can think that this continues for a long time. And it doesn't finish there because the 3-point ladder is the first part of Cyc. This is about 20% of the runtime. Later you have another 80% of the runtime when a similar thing continues. So it becomes awfully easy to notice with side channels. Of course, a natural question to ask is, okay, how do we defend from that? Well, the one way to defend it is pretty easy. If you look at it closely, you will see that the problem, or one of the problems, is that the points that are generated maliciously. they don't satisfy, among the other things, they don't satisfy an order formula or independence. I didn't explain what independence was, but you can think like they're of incorrect order. So if you check that they're of correct order and that the 3 input points are independent, and this is not difficult to check, then we have shown in our paper that you will never get a single 0 throughout the whole computation of Cyc. So it's a good way to defend from the whole attack. However, there's a problem with this countermeasure. I mean, the problem is the cost. It's around 10%. And Cyc, well, I didn't mention this in the beginning, but Cyc has some drawbacks. Is that it is the slowest of all post-quantum algorithms, but it also has the smallest keys. But it is slow, so this additional overhead is just, you know, it's a bigger problem than it would be for some other algorithms. Now, before I finish, I wanted to mention 3 more things. The first thing is how does Cyc compare to ECDH? So this is my point of view, like why this attack happens. Well, ECDH, first of all, elliptic curve Diffie-Hellman, it has only one curve. So in elliptic curve Diffie-Hellman, you don't get to choose a curve. You get one curve. This curve is hard-coded into the algorithm. It's not that somebody gives you the coordinates of the curve. No, it's saved in memory already, and you cannot mess with it. In Cyc, there are many curves. In an honest execution of Cyc, you expect to get some random curve, right? And that just means there's a bigger surface of attack. Another problem is that the curves in elliptic curve Diffie-Hellman, they're fixed, but they have an order which is, let me call it nice. So the order is a large prime number, or at most a small multiple of a large prime number. I don't know a single curve which is used in crypto and does not have one of these 3 orders. So Q, 4Q, or 8Q. On the other hand, in Cyc, the order is highly factorizable. So it's a multiple of a large power of 2 and a large power of 3. And this is if you're being honest. However, Cyc doesn't check the order of the curve when you receive it as an input. So if you're malicious, you could take a curve of a different order. And there are many curves. So who knows what other malicious things you could do. Third thing, elliptic curve Diffie-Hellman uses only one point for input. So if you remember Diffie-Hellman, I send you g, you compute g to the x. Or I send you an elliptic curve point, you compute x times that elliptic curve point. Well, for Cyc, it's not the same. For Cyc, you get 3 points. And you need to set at least 2. So this also becomes a problem. This is actually the reason why we cannot, like we couldn't do this attack that I just presented in ECDH. Among other reasons, because there's only one input point. And this input point, not only there's only one of it, it has a small number of orders that you could choose from. Like if it's on the curve, then it has one of these 4 orders, because Q is a large prime, so you don't really divide Q by something other than Q itself and 1. In Cyc, we get the previous problem again. Since the order is so highly factorizable, you can get points of many different orders. So this would be something like 250 times 150 different possibilities for orders for points on Cyc. And again, if you're being honest with the curve. And finally, in ECDH, if you want to check that the point is in correct order, that's easy. You can do it in negligible time. But in Cyc, this cause, well, actually, I just noticed that this was wrong, what I've written in this slide. I wrote that the check that the points are honestly generated is costly. No, the check that the points are of correct order is costly, and it is around 10% of runtime. But you don't get honesty. You don't get the proof that they're honestly generated. They could be of the correct order, but there could be something else malicious done on them. And as far as I know, and I believe that it's probably very hard to prove that points are honestly generated. Probably as hard as breaking Cyc. Okay, so second thing, before I wrap up, I mentioned that we did 2 attacks. One attack on the 3-point ladder and another attack on the isogeny. And both attacks are similar in that we force this avalanche effect. So we force the computation of a point 0, 0, and then there's an avalanche effect. However, I believe that there are some deep differences in how these 2 things happen in the 2 cases. In the 3-point ladder, the problem is that the formula is not complete. And I guess some people know what that means. I'm not going to get into explaining that. This is, on one side, it's unavoidable on elliptic curves. On the other side, it can be avoided. And again, and this makes sense, what I just said. And so if you think about it, we computed something which makes sense. We added 2 elliptic curve points. It was the formula that was the problem. The formula at these 2 points, it gives you 0, 0. And actually, if you go deeper into it, those 2 zeros, they cancel out in a smart way, and you can get something which is meaningful. In the second attack, the isogeny attack, the problem is deeper. We force the target to compute something completely nonsensical. And it computes things which don't make sense, like points which are not on the elliptic curve, isogenies which have bad kernel, things which are not algebraic, and then it just messes up so much that you get a 0, 0 in the end. So I think, if you think about this, that there is more to be analyzed in the isogeny, and there are some additional threats coming from there. And now to end, I just wanted to explain how the Hertz bleed attack works. So a couple of weeks ago, this new attack on Intel processors was published. This was not done by me, so this was done by a different team, but they used the same exact attack that I just showed you as a proof of concept for an attack, for a timing attack on x86 processors. So I presented a power analysis attack, and they exploited a weakness of x86 to translate this attack to a timing attack. So how is this done? Well, essentially, they target processors, x86 processors, with turbo boost. And turbo boost is important here. Turbo boost and dynamic voltage and frequency scaling. So what is DVFS? Essentially, you can think about it this way. You have a processor, it clocks at 4 gigahertz. And then you turn on DVFS. And DVFS says, okay, I'm going to allow you to work between 3 gigahertz and 5 gigahertz. Because I'm good. And of course, you say, well, I mean, that's great. I'm just going to start pumping at 5 gigahertz because I want to be faster. I want to do more. And it starts computing a lot faster. But there can be problems with that. For example, you can start running out of battery. Because if you compute faster, you use more energy. Or you could start overheating. And so if you start overheating, the controller steps in and says, oh, wait, the CPU temperature is too high. You cannot continue computing at 5 gigahertz because you're gonna burn. So let me lower the frequency to 3 gigahertz so that it cools down, and then I can let you compute fast later again. And this, I think, in essence, can be captured in 2 formulas. First one is that the power is proportional to the voltage squared times frequency. And the second formula is that the voltage is proportional to the Hamming weight of the machine words in memory, or to the Hamming distance between consecutive machine words, or you can think about it to the number of bits that are flipped. When you flip bits, you need to use an energy to flip a bit or to write a 0, so it's proportional to V. And so it essentially works in the following way. Suppose you have a lot of bits to flip, right? Well, you flip more bits, you need more current. Well, if you need more current, you increase the power. And if you increase the power, the temperature of the CPU increases. But if the temperature increases, then the controller steps in and says, okay, you're overheating, I need to lower the frequency. But if you lower the frequency, you increase the runtime, because that is what frequency means. And therefore, you can extend this attack really easily. So if you remember the attack from a couple of slides before, if your secret key bit is 0, then you compute the projected point 0, 0. But if you compute the projected point 0, 0, you get the avalanche effect. What does that mean? All the variables are 0. All the variables are 0. You never flip a single bit. So you use less current, and you can obtain a faster runtime. On the other hand, if a secret key bit is 1, then all the variables are, you don't get a 0, 0. You get random, and all the variables are random, and all the Hamming weights are random, and you flip bits, and you use more current, and you get a slower runtime. And this difference in runtimes, it's not stark. It's not like you get a second more, but you can definitely notice it if you run the attack enough times. So this is from the Hertzbleed paper, and this is a histogram of the runtimes for the two cases when a secret key bit is equal to 1 and when a secret key bit is equal to 0. So yeah, sometimes one can be faster than the other, but on average, if you have more zeros, you're going to be faster. And this simply shows how to extend a power analysis attack to a timing attack, and therefore to a long distance attack, and so on. But also, as I said before, you do the point order check and you fix it. And this covers my talk. Thank you for your attention.
We see some hands clapping up on the thing, just to...
Oh, thank you.
And thanks very much, Novak. We might have time for the isogeny part if you're happy to do that, but I'll ask if anyone wants to ask questions at this point, if that's all right.
Yes, of course.
So yeah, any questions from the audience here or from the audience online? You can either type them into the chat and I'll relay them, or you can unmute and ask your question directly if you like. Any questions out there? Check the chat. Oh, a bunch of applause. Great. Okay, so I've only got one question at this point. The performance of using Montgomery is basically identical to using Edwards, roughly speaking.
Okay.
Plus epsilon, one or the other. So I think the points of small order on the Edwards curve, if it's defined in the right way, don't have any zero values. With that, I don't know.
Yeah, I mean that's what Edwards coordinates do. You kind of make the formula complete by moving them in an extension.
Yeah, the points of infinity are buried off in the extension field. So might it be wise just to switch the whole library over to Edwards?
Well, I guess you could defend from the 3-point ladder, but I don't think you could defend from the isogeny attack. And also, I don't know how these formulas look on the isogenies.
Yeah.
Because you fixed the problem of formulas being complete. That's not the only problem. So this is just like this only fixes the addition formula which is complete.
Right.
The isogeny can also output a 0, 0. And I don't know how.
You can get garbage on that. So.
Yeah, exactly. So I'm not sure. I don't even know how isogeny formulas look on Edwards curve. Would there be as efficient?
Very similar.
Similar.
So that's probably not. Yeah. And I'm also not sure that when the curve has such a smooth order like that, if you still get to vary the points of infinity.
Yeah, it's kind of odd because this is like. Kind of important at that point. You use these. Yeah, I don't know if you could throw it out at an extension field because you use points that are above it. P or Q, one of the two or
Right.
is above it. So it definitely cannot be in an extension field, but maybe something.
Maybe.
Yeah, I didn't think about that. Yeah.
Cool. Usually I'd say thanks again and wrap up, but I'm keen to hear the other slides if you're happy to talk through.
I will.
Yeah. For those online, we're going to continue with the auxiliary part of the talk, which is to hear more about the isogeny attack. So yeah, we'll carry on since we've got time. That'd be great if you don't mind.
Okay. Yeah. So these are the people from the Hardsby paper. So I want to give them credit for their work. So let me jump over this. Outline of the isogeny attack. So the idea is that I want to force the kernel generating point of the isogeny to have order a power of 2 when you compute the 3 isogeny. So you can also attack the 2 isogeny with a power of 3 point, or any L isogeny with an L prime order point. And we showed that there is a special number called the breaking point, such that if the order of this point is 2 to the r, well, when r is smaller than the breaking point, then you always get 0 value and avalanche. If the order of the point is to the r with r greater than the breaking point, then you get no 0 values and everything is random. And this you can do in 2 steps. So I'll show first how to force the order to be the way we want it. So we can force the order of the kernel generating point to be 2 to the r minus 1, plus 1 or plus 0, essentially depending on the secret key bit. So either 2 to the r or 2 to the r minus 1 for any r. And in particular, we're going to use 2 to the o or 2 to the o minus 1 to always fall into one of these 2 cases, depending on the secret bit. And once you have that, then we'll show what happens if r is of this bad order. How and why do you get all those zeros? Order forcing is it's very simple, but the formulas look large. Essentially, you take a point of order 2 to the r minus 1, and then you kind of want that to be p. And then you take q to be an independent point of order 2 to the r plus k, where k is the bit that you want to compute. And then you update p by subtracting the known secret key part of q, because you want to get rid of this. You want to start from bit k, right? And so when you compute p plus skq now, well, p is the point of order 2 to the r minus 1 minus this then q, and q you just develop sk, the whole sk. So this is the known part, and this is starting from the k bits upwards. And of course, these two cancel out. So the minus known part and the known part. And you're left with s, point of order 2 to the r minus 1, 2 to the k times q, which this kind of k cancels out, so you get a point of order 2 to the r. And then another, like the remainder, which is a point of order 2 to the r minus 1 or smaller. Because this would be like 2 to the k plus 1 times q, so you lose k plus 1 in the exponent of the order, right? So this you can kind of ignore. And you get either s, which is a point of 2 to the r minus 1, plus a point of order 2 to the r, if the secret key bit is 1. So you get a point of order 2 to the r, right? Or if this is 0, you get a point of order 2 to the r minus 1, and then another point, but which is independent from it, so they really can't cancel out. You don't care. And therefore, you can control, you can do the trick. If you know the previous bits, based on this next bit, you can control the order of the kernel point. It's either 2 to the r minus 1 or 2 to the r. And this is for every r, almost every r. I mean, it's maybe not when r is higher than what is the size of the curve, something like that, but almost all r's. Okay, and that was simple, but what happens during isogeny computation? So isogeny, it would works as follows. So let's say Bob, who's the target, computes a 3 to the i3 isogeny. And an isogeny is, I mean, you know this, but I didn't remove it from the slides. It is a hard-coded sequence of the following operations. You do triplings on an elliptic curve. You take a kernel point of order 3. You compute the image curve through a 3 isogeny. And then, with the same isogeny, you can push some point onto the next curve. And another thing is you can save and load a point. These are the 4 operations which are used in isogeny computation, and the order in which you do them is saved in what is called a strategy. So for example, how does it look to compute an isogeny of degree 3 to the power 7? Let's say you start at some curve E0 and you have some point R on this curve. Well, you take this point and you start multiplying it with 3. So you compute 3R, 9R, 27R, so on and so on and so on, until you get to obtain a point of order 3, which is 3 to the 6 times R. You use this point as kernel to compute the next curve, and then you start computing isogenies to push some saved points to the next curve. Then you do the same with the next point, next curve, push points. Then you do the save, and sometimes you might have to triple a point. And so on until you get to the final curve and you finish your isogeny computation. So this thing can be very nicely represented in a tree. So what happens if a kernel has a bad order? Like if this point R is not of the order 3 to the 7 or 3 to the whatever it needs to be. Well, you're on the starting curve, you triple R. So even if it's of the bad order, you're still going to triple it, and it's going to work, right? And some of these points which are triple, they're going to be saved. And this is still okay. But then you start computing a 3 isogeny. And this is the first problem. So you compute a 3 isogeny, but your point is of the bad order. What happens? Well, what happens is that you get something nonsensical, right? You're going to get a random curve, and you're going to get random image points. The image points don't have to be on the curve. The curve doesn't have to be isogynous. It doesn't have to be supersingular. It doesn't have to be a curve. I mean, it's going to be a curve because you get a coefficient, but it doesn't make sense. Then you're going to stay random until the end of the protocol, because then you're not even on elliptic curves. You just compute random stuff with random things, right? So you kind of expect to get all random things until the end of Cyc. You do, except in some cases. So there are some things which are not random, and this is kind of expected. It makes sense. Like, even if an isogeny is a nonsensical isogeny with a nonsensical kernel, it's going to send the point of infinity to point of infinity because of the way they're constructed. Even if the isogeny is a nonsensical isogeny, if the kernel point of the isogeny is equal to the input point of the isogeny, the output point is going to be the point of infinity. Which, yeah, it kind of makes sense. You want, isogenies need to have that property for good kernel points. So it happens also if the kernel points are bad. And then there's one property which is formula related, is that if your kernel is the point of infinity, then you get a degenerate curve. Degenerate curve, it means the curve of coefficient equal 1 divided by 0. And then however you represent that in projective coordinates. There are different representations. And the final property is that if you happen to compute a 0, and if you happen to be on the degenerate curve, and if you just so happen to triple that point 0 on the degenerate curve, well, you're going to get 0, 0. And this is what we can get. So how does that work? Well, there is a nice if and only if for getting that 0, 0. 0, 0 happens if and only if one of the two following properties. Either two of the points which are saved on the starting curve are equal, or if two of the points are different by t. Probably remember what t was. If they have flipped coordinates, but this has also a deeper algebraic meaning, is that one is equal to the other one plus that point t 0, 1 for 2. So let me just explain the first case, but the other case is essentially identical. What happens if you have two equal points on the starting curve which are saved? Well, they're going to be sent to the same points with the isogeny. Even though the isogeny is nonsensical, it's a function, and a function sends the same thing to the same thing. It's what the definition of a function is. And since they're going to preserve this equality, eventually one of them is going to be used to compute an isogeny as a kernel point, the image of one of it, right? Well, when you use it as a kernel point, then you're going to send the other point to the point at infinity because of the property mentioned in the previous slide. And that point at infinity is going to be preserved because you're going to push it with isogenies to the point at infinity. You're going to triple it to the point at infinity. So it's just going to stay there until eventually you use it to compute an isogeny. Use it as a kernel. So you compute that isogeny, and the image curve is going to be degenerate. But then you're going to also push that 0 to the image curve, and eventually you're going to triple it, and eventually you're going to get that 0, 0. And I have a very nice explanation of how that actually looks. So let's start off with a point of a bad order on the curve, where we want to compute an isogeny of 3 to the power 10. So we triple, until we get to what we expect to be a point of order 3, but is essentially a point of order 2 to the something. And let's suppose that these two large points, the fat ones, this one, are equal. Well, we use this point to compute an isogeny. And what happens? Well, the next curve is random, not a curve. Blue means nonsensical. So we push the first point to something random. We push the large point to something random, but the other large point goes to the same thing. So fat means equal. We push this point to something random, and we continue. Now again, compute an isogeny. Random point, random isogeny, nonsensical. Everything stays blue, but the fat point stays fat. Now compute an isogeny with one of the two equal points. The curve is again something random because the point is random itself. But the image of the other point becomes a point at infinity represented in light blue. And now we continue. Take this point at infinity. Triple it. We're on a random curve, so tripling is good. I mean, you're going to get still the point at infinity. Triple. Oh, it's the kernel of a isogeny. Compute an isogeny. Bam, you get a degenerate curve represented as blue. So we continue. You push the random point. Happens to be a random point. You push the point at infinity into the point at infinity. But now, and then you do another isogeny. And it stays the same because the isogeny again has 0 for a kernel, so the next curve is degenerate. You push these two things, and finally you need to triple the point at infinity at a degenerate curve. What do you get? You get the point 0, 0. What happens when you get the point 0, 0? Everything becomes 0. All isogenies, all points, all curves are 0, 0. And this will happen until the end of the algorithm. Usually, this happens like in the first 20 to 30% of this graph, but I might even show you later one of the pictures of that. And finally, how do we get two equal points on the starting curve? Well, that's pretty simple, because if you think about it, what are the saved points? Like they're saved in the isogeny. It's simply some indices I such that 3 to the I are is saved. So like it's 10 points usually, or log of E, 3 points. And when are 2 points equal? They're equal if and only if 3 to the alpha R equals 3 to the beta R for some alpha beta in the index set. And somebody will say, yeah, plus minus. Yeah, plus minus. Let's not be too detailed here. And what is this? Well, this is just a modular equation. Because if the point R is of some order 2 to the R, then this is just a modular equation modulo 2 to the R. And what happens is that not only is it just a modular equations, but if you have a solution modulo 2 to the R, you will have a solution modulo 2 to the R minus 1. Because it projects. And therefore, if you have the strategy, and the strategy is public, you can show that there is this breaking point. You can always find some R which is so large that for any pair of indices, this formula here becomes non-zero. And therefore, if it's true for R, it's true for all the exponents larger than R. And you will be able to find some R where this equation is equal to 0, so it will be equal to 0 from R onwards down up to R is equal to 0. If you think about it, let's say R is equal to 0. What does that mean? That means the point is a point at infinity. Well, of course it's going to repeat, right? Because you triple it into itself. So there's always some solution. But the more you go up, eventually you're going to run out of solution. And like you can even get a heuristic argument why that is always going to be the same, because you have a small number of indices, but the exponent is so large, so you don't expect to get an equality here. And also you can like factor this out, so I don't think, maybe you could do like a very inefficient strategy to try to fix this, but you can't run away from it. And this doesn't actually only work, as I said before, on the 3 isogeny. It works on the 2 isogeny, on the 3 isogeny, on any L isogeny, on any curve which has an L and L prime isogeny. You can do this attack. And in particular, these are the exponents for these parameters of psych. And here, the exponent is very low because in this curve, if you remember, like the 2 isogenies are actually computed with 4 isogenies. But on this curve, you do the 2 isogeny in the first step, and later you do the 4 isogenies. And that, we thought it was going to be problematic, but actually it's even easier to attack that. And for the end, this is how it looks. It's not so clear, the picture, but this is how it looks in practice. So this is a 3 to the 137, so this is the smallest parameter set of psych. We send a point of order 2 to the 8. And the point of order 2 to the 9 would have everything dark blue until the end. So everything would be completely random. A point of order 2 to the 8, this point here denoted with a star, if you can zoom in enough. And this saved point here denoted with a star, they happen to be equal. So when this isogeny is computed, pushes it to the point of infinity, propagates, blah, 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 and eventually over here, if you zoom in enough, you get a small first red isogeny and 0.00, and then it's going to propagate until the end. And that's it. And well, since I just have a couple more slides, I can just add it. How we attack this with side channel is that we just computed 2 baselines. Essentially, we gave you something which is always going to be 0, independent of your secret key, and then we give you something which is never 0, independent of your secret key. And then we just correlate this power trace with the power trace extracted for each bits. And what we get when we compute this correlation is the following. So either you get the correlation of 0.99 where you're correct, or 0.3 when you're incorrect. So it's pretty easy to attack. And that covers the isogeny attack and my presentation. Thank you.
Thanks again. All right, I'll pass quickly to the audience once again in case any new questions have popped up. And let me check the chat. You can also unmute again if you want to chime in with a question, anyone.
Just very clean present.
Yeah, absolutely.
Thank you.
Okay. If not, let's thank Novak again.